So if you're having to watch this video from at home, we just talked a little bit about conservation of momentum. We're going to look at the theory development of this now. And so even if you're having to watch this video from this point on, the theory development is good. The conservation of momentum stems from Newton's third law and the impulse momentum theorem. Now, yesterday I showed you guys when a rock climber falls from the rock, the impulse delivered is going to be spread out. That time is going to increase to lessen the amount of force acting. In this case here, the red car or the blue car, sorry, the green car and the tan car collide. They hit each other with equal but opposite forces. Newton's third law says no matter how complicated this force is, the other car has to hit with the exact same amount of force for the same amount of time. Now, impulse in this case would be represented by the area underneath that curve. So that impulse is the product of force and time. F1 multiplied by that time would be sort of a positive impulse. And because Newton's third law says F2 has to exert the exact same amount of force for the exact same amount of time, this would end up being a negative impulse. And when I add those two together, you get 0. So the idea behind that is that the total impulse delivered to the system is a whopping 0. Overall, there is no change to the momentum of the entire system. Each object may change its momentum, but the system's momentum is conserved. No change in the overall system's momentum. So the development of the law of conservation of momentum is derived on Newton's third law, which says forces always come in pairs, and Newton's second law, which is related to the impulse momentum theorem. As an equation, I'm going to write that down for you so you guys can use this equation to solve conservation of momentum problems. It's a really simple equation to write. Summation, because systems usually contain more than one object. And so we would sum all of the momentum of the objects prior to the collision, and that would be equal to the sum of all the momentum of the objects after the collision. Now, we're going to expand that equation. I'm going to show you how we would expand that with a variety of examples. But that's the basic idea. So it's derived from Newton's third law and Newton's second law. Now, there's 3 different kinds of scenarios that we typically look at for conservation of momentum. They are big on collisions and explosions. So the application is related to objects colliding and objects exploding. And the reason for that is that the forces involved are usually too hard to quantify. We can't describe those forces of collision very easily at all. It's too hard to model with other things, so we don't worry about what those forces are. We just use impulse momentum theorem to show that the momentum is conserved from beginning to end. Now, I'm going to demonstrate these things here with the cars on the track. Hit and stick is also called a perfectly inelastic collision, so we'll study that stuff more tomorrow. So perfectly inelastic. When objects hit, deform, and sort of stay moving together. So perfectly inelastic. The idea here is that one object sort of becomes 2 objects. So we might have A coming in, colliding with object B. During that collision, object A and B collide. We have a transfer of momentum going on. And then afterwards, they move together with a common velocity afterwards. So this might be V initial, and this might be V final. So the objects combine. They move as one object. Very common examples are football players tackling each other where they have a combined speed afterwards. Now, hit and rebound, the typical situation here is that we have one object coming in, A, collides with object B, and then each object moves separately after the collision. Sometimes they move in the same direction. Sometimes we have them move in the opposite direction. And sometimes what happens is A might stop and B goes off. But in all cases, whenever that happens, they hit, they bounce off each other and they move with their own separate velocities afterwards. Go ahead.
Well, if A stops, isn't that just the same as the first one?
No, because perfectly inelastic means they combine and move together.
Oh.
Yeah, so hit and rebound means that when we go to write the equations, you'll see how we write these things. When we go to write them, we have to look at what happens before and then what happens after. This portion right here is really complicated to describe because we don't really know what happens during that interaction. It's a very short time interval. We can't describe those forces really well, so all we do is we look at the before and we look at the after. Momentum conservation says regardless of what happens to A, B must basically cancel that impact because that momentum is conserved. So we can't describe those interactions really well. And then for explosions, usually what we have for explosions is that we have objects that are sort of combined together, they push off each other, and they acquire equal but opposite momentum, like so. So explosions have something like this, where usually P initial is 0, and P final is 0. Usually that's the case, that whatever we start with, we end with, but usually things are at rest and then they explode away from each other and they acquire equal but opposite momentum. Now I'm going to show you how to write the equations and solve some problems with that, but it's really those three types. I'd like to do a quick little demonstration for you. Come on around this table for just a few minutes if you would. I'd like you to see these firsthand. Now, because I'm recording this, I'm going to try to use this one here. Hopefully I don't have anyone actually get in the video recording, and that's because then I can't place it on YouTube, so I don't want to do that. So let's try this here. Ooh, your leg is there. Okay, could I have could I have all you guys get up, because I might want to place this on YouTube, and I really can't have students on that thing. So I'm going to have you get up so I can see this here. Okay. All right, now I'm going to zoom in a little bit. So what I want to do is I want to show you these collisions with this set of cars and tracks here. Okay. Now, let's see. Where's my? You guys have seen this before. Okay. Can you see it up there? Is it on the? Okay. So this is all about momentum transfers, right? So we have one object coming in, it goes to the other one, and then sure enough, you can see that whatever the incoming momentum is, the other ball goes out with the same amount of momentum. So all we're doing is we're just transferring that momentum from one object to the next. I'm going to do 2 of those. And so somehow it knows that I sent in 2 balls. So it sends in 2, it sends out 2. It can do 3. So this is always sort of fun. So when I send in 3, somehow it knows to send 3 out. And then, of course, when I send in 4, somehow it knows to allow 4 to keep going. How it knows that is because both momentum is conserved and also very closely is kinetic energy. I think it can even do 5. We'll try that. Okay. Thank you for the laugh. They're laughing right now. All right. Now, what's sort of fun on this, and I'm going to try this one here. You guys can sort of see it. Much better camera. All right. So I'm going to try to do 3 and 2 like this. It's always fun. They're super excited. I can see that. All right. Now, what I want to do is I want to show you this with collisions here, and I'm going to do this with these cars. Now I'm going to show you the exact same thing. These are magnetic cars, and so when these things collide, they're not going to actually collide with any sound. And so these things have magnets on them. And so when I go to do this, I'm going to zoom out just a little bit. Video recording always makes it tough. Okay, good. We still can't see anyone. So I'm going to come down here, and I want you to see the momentum transfer from one car to the next as I go through and do this. And you can see that there's no sound being created. And so during that collision, momentum is being transferred from one car to the next. And this is essentially a larger version of the exact same thing that you see there. I send in 1 car, and when I'm all done, I send 1 car out. If I were to send in 2 cars, are you guys ready? I'm going to send in 2 cars. You guys see that at the end, those two are moving, and those things have completely stopped. Let me try 3 cars. Are you guys ready? So I'm going to send in all 3. And when I'm done, I see that 3 were still continuing to move. These are sort of the hit and rebound kinds of problems. Now, what I'd like to do is I'd like to show you the hit and stick one. So the hit and stick, what I'm going to do is I'm going to use the ones that have some Velcro on here. And so these also have spring-loaded mechanism in there, but I'm going to go ahead and compress these. And so now, let's see if we can do some math here. When this one comes in, you can see that the mass became twice as massive. Can you guys see it? One more time. This car comes in with a certain amount of momentum, and after they collide, can you guys see that they travel with about half the speed? So twice the mass moving at half the speed would have the exact same amount of momentum. Okay, so let's try this. This thing's coming in with, let's see, this is 500 grams, that's 500 grams. This thing's coming in at 5 meters per second. How fast do they leave? 2.5 meters per second. Okay. Twice the mass moving at half that speed would have the same amount of momentum. Okay, let's try this one. This one comes in with 5 units of momentum. How much momentum did this one acquire? 5. Okay, now I'm going to change some masses here. So in this case here, I need back there I have some black bars. Those black bars represent, each one of those things is the entire weight of one of these cars. So again, you guys can see this. This one's going to come in with 5 units. What do you think will happen after it collides with this? It's more massive. Do you think it will completely stop, continue to move, or go backwards? What do you think will happen? Okay, so at the same speed as this one here. Now these are not going to stick together. These are going to be hit and rebound ones, right? So when I have equal masses, so again, equal masses, I see that one transferred all of its momentum. Would you guys agree all of its momentum was transferred? So this is a hit and rebound with equal masses. That one stopped, that one acquired the same speed. Now what I'm going to do is I'm going to make this one twice as massive. What's your gut tell you is going to happen when it collides? It's going to keep going in the same direction as it was going. I'm going to do some math here. I'm going to show you guys that the math is not too difficult. This one comes in with 5 units, and it continues to move. Do you guys see that it continues to move? It's got mass. Mass sort of protects its motion. So let's try this again. This comes in with 5 units, and it continues with 1. How much did that one acquire? Watch it again. Comes in with 5, and it continues with 1. How much did this one have to get? 4. The system momentum is 5 before, and it's 5 afterwards. 1 plus 4 is 5. You guys see it? Okay. I'm going to change this around to be like this. I'm going to have the light object hit the heavy object. What do you think it's going to do? It's going to rebound. This one's got a lot of mass. This one has little mass. Its motion is not very well protected. So it's going to be able to change its motion quite a bit. It comes in with 5, and you guys see that bounces back? It comes in with 5, and it leaves with 1. How much did this one get? It comes in with 5, and it leaves with, so watch it one more time. It comes in with 5, and it leaves with 1 that way. How much did this one acquire if momentum is conserved? 6. Because there's a direction associated with it. Let's do, now, guys, this is the hard part of momentum conservation. The system momentum is 5 towards Logan. Afterwards, the momentum must be 5 towards Logan. If this acquires a momentum of 1 that way, that one has to be 6. So that 6 minus 1 is still 5. You guys see that? So you guys see, that's how that math works. Vector. Momentum is a vector. Now, this one comes in with 5, and it leaves with 1 that way. What was its change in momentum? What was its change? 6 that way. How much did that one have to acquire? 6 that way. So the total change is 0. You guys see that? Okay. That's the hard part that people will have with solving the equations for it. I want to do one more, which is an explosion. So explosions, they deal with ones with the spring. Okay, so these have springs in them. Now, I also have Velcro there, so I'm going to go ahead and stick these things together. I'm going to place this at a 60 centimeter mark. Now, this is a 120 centimeter long table. When I trigger this, this one's going to be shot out that way, that one's going to be shot out that way. How should their speeds compare? Should be the same. Because if the momentum is 0 to begin with, when I trigger these, will you stop that one from going off the edge? I'm going to stop this one. When I trigger these, they should acquire equal but opposite momentum. Since they have the same mass, they should acquire equal but opposite speed. They should get to the end of the tracks at the same time. And sure enough, they did, right? They go. Okay, so what was the momentum after the collision, or after the explosion? How much momentum did the system have? You guys ready? After the explosion, how much momentum did the system have? 0. If that one acquired 5, that one acquired 5. When I add them together, I get 0. Okay. Now I'm going to change the mass of this. I'm going to make this one twice as massive as this one. What you guys have to do is you have to figure out where to place these things such that they will get to the end of the tracks at the same time. You guys understand the idea? If I do this here, one of these is obviously going to go off faster than the other one, correct? Which one's going to go off faster? The lighter one. How much faster? It should be twice, because that mass times twice the velocity should be twice the mass times half that velocity, right? You have to figure out where to place this junction so that they will get to the end of the tracks at the same time. You understand that idea? Okay. Head back to your table. You're going to solve that as a table group, and we're going to see whether or not that works. All right. Oh my gosh! All right. Now I'm taking the camera away, so we don't have to worry about the camera students on there. So what I want to know is where to place that interface between those cars so that they will get to the end of the track at the same time. What do you need to know to be able to do that? The combined length of the cars is 34 centimeters. The combined length of the car is 34 centimeters. This is a 120 centimeter long track. I want to see if you guys can work through the math there to determine where to place the middle of this so that they will get to the end of the track at the same time. If you're trying that at home, because you're watching this video from there, your same idea. It's a 120 centimeter track. The cars are 34 centimeters in length, and you have to figure out where to place those things so that they will get to the end of the track at the same time. The combined length of the track the cars have to travel on the track would be the difference between 120 and 34. What is that number? 86. So 86 has to be broken up into 2 different kinds of motions, right? 2 different lengths. One of those has to be twice the other, correct? Could you just do this as 2x plus x is equal to 86? Solve that for x? So one of them is going to travel twice as far as the other. The goal of algebra oftentimes is to introduce a variable that variable represents something. In this case, x represents how far the car is going to travel. So what is that? 3x is equal to 86. What is that number? 28, roughly 29 centimeters. Okay, so what we're going to do, x would be equal to that. What we'll do is we'll place this thing such that this car will travel 29 centimeters. Let's change the order of this. It's easier for me to do on this side. So this car will travel 29 centimeters. The lighter car is going to have to then travel with that 58 centimeters. We're going to check to see whether or not when we explode this, that one will travel that distance in the time that this one will travel that one. So it's a little qualitative demonstration that momentum is conserved in this explosion. You guys ready? Try this. Did they get there roughly at the same time? Those of you that were up close? Sure enough, you can sort of see that. Okay. All right. All right, guys. And the next thing that we're going to look at is I'm going to show you guys. We don't have a lot of time, but I want to show you how you might set up something like this one here. And so let's see. I'll probably run out of time here. It's 1:44. Let me see where we are. I'm going to go to 1:47. I think what I might do is I might save these problems till tomorrow. Okay. Now, if you do have some problems for you guys to look at, you'll see that this isn't too difficult to do as we go through it. But because I'm running out of time, we'll save that for tomorrow.